Writing and interpreting parametric solutions to a system. So we saw before that typically systems have one solution once we solve them with Gauss-Jordan elimination. So here we would see, oh, this is just a point. The point 4, 2, 8 is the solution to the system. And this is because you see here what we have is the identity matrix. The identity matrix, once again, is a square matrix where along the diagonal are all ones and everything else is 0. So x equals 4, y equals 2, z equals 8. Very nice and neat. But here we have 4 cases where we don't have that. So here, what's different is that there's this 0 in z instead of a 1. Actually, all of these cases are where one of the variables, at least, is missing. Here we see that it's equal to 1, which we can't have 0 equal to 1. Here we have 0 equals 0, which is always true. And there are variations on 0 equals 0. So these give us different versions of what the parametric system will look like. So the solution set. So first of all, what this means, let's write these equations out. X equals 4, y equals 2, 0 equals 1. When does this happen? Well, when is 0 equal to 1? That's no solution. Here we have x equals 4, y equals 2, and this is 0 equals 0. When does that happen? Always. So this is infinitely many solutions. So this is the system where x equals 4 and y equals 2. Now, if you have noticed, that is a line, because those are all the coordinates where x is 4, y is 2, and z can be anything. Here we have x plus 6y plus 3z equals 4, 0 equals 0, and 0 equals 0. So these are useless equations. I mean, they're true, but they don't help us. And that is the equation of a plane. The normal vector being 1, 6, 3. Here is one way we could have a system where, well, all of the equations were essentially the same, because if you take 3 planes and have them all intersect in a plane, then they have to have been the same plane. And lastly, here we have x plus 3z equals 4, y minus z equals 2, and we can't actually figure out from here what z is. So this is where we start setting up parametric equations, and this is another line. So this was a line. This was the line. The line where x is 4 and y is 2. But this is going to be a line that we're going to need to write in parametric form, or symmetric form, but typically parametric is going to be easier for this purpose. So once again, if each row represents a one variable solution, like 0, 0, 1, 3, then there's one solution. So that was what we had here. One solution. If any row represents a false equation, like 0, 0, 0, 2, then there's no solution. So that was this one has 0 solutions. Otherwise, there are infinitely many solutions. So this has infinitely many solutions, this has infinitely many solutions, this has infinitely many solutions. But infinitely many solutions can be multiple things. Here we said this was a plane because that's a single equation with 3 variables. Here we have 2 separate equations with 3 variables total. That is a line. So the question is, how do we How do we write that afterward? Well, when it's a plane, we just leave our answer as the equation of the plane. That's what we did here. But when the solution set is a line, we have to go a little further. We have to define a parameter, substitute the parameter into the equations, solve for the other variables, and write your answer in parametric form. So typically, I'll use the parameter t. The text that I shared online typically uses a. So we're going to substitute the parameter into the equations, solve for the other variables, and write the answer in parametric form. So here we have x plus 3z equals 5, y plus 2z equals 8. So I'm going to set the parameter z to be equal to t. So what that means is we can plug in t for those two equations. So the first one will look like x plus 3t equals 5. And now I'm going to solve for x. X equals 5 minus 3t. Do the same thing for y. Y plus 2t equals 8. Y equals 8 minus 2t. So now we have a set of three equations that are in parametric form. We already have the x, y minus 2t, and then the z is just t. So this is the parametric form of a line. We learned how to convert it into symmetric form in the previous unit if you want to do so, but this is how we write it in parametric form. Here's another example. We have x minus z equals 12. We have y plus 4z equals 6. So let's set a variable to be a parameter. Typically, I'll choose z. Whatever appears more than once is typically the easiest thing to do. So we'll have x minus t equals 12, and y plus 4t equals 6. When I add t to both sides, I get x equals 12 plus t. I get y equals 6 minus 4t, and we already had z equals t. So here is the parametric solution to this system. Thanks.